Welcome to the Deep Dive. Today, we're going to be tackling this paper titled Fractional p-Laplacians via Neumann Problems in Unbounded Metric Measure Spaces. And wow, this one is dense.
It really is, yeah. It's a very interesting paper, though. The authors did a really nice job of kind of connecting some different areas of analysis to come up with a new way of looking at these fractional p-Laplacians.
So I guess, even just starting with the title, right? There's a lot there. We've got fractional p-Laplacians, Neumann problems, unbounded metric measure spaces. Like, where do we even start unpacking this?
Yeah, it is a mouthful. Maybe we should start with the fractional p-Laplacian, which is kind of the heart of the matter here. And I guess one way to think about it is that it's like a generalization of the usual Laplacian that you're familiar with, but instead of measuring like the average change of a function at a point, it's kind of measuring interactions over distances. So you can kind of imagine like modeling heat diffusion in a material, for example, but where the heat can kind of jump between points that aren't immediately adjacent.
Okay, so it's not like smooth, continuous diffusion. It's more like a little more erratic.
Right, yeah, exactly, yeah. And that's kind of where this fractional part comes in. The fractional p-Laplacian is often denoted by this sub where tau p is between 0 and 1. And this news kind of lets you fine-tune how non-local this interaction is. So the smaller the s's, the more pronounced these long-range effects become.
Interesting. So where do the Neumann problems fit into all of this? I know they deal with boundary conditions, but I'm not sure how they connect to these fractional operators.
Right. So the authors are working with Neumann problems for the Laplace equation, but they're looking at it in this very specific setting. And that's where these unbounded metric measure spaces come in. So instead of like a traditional Euclidean domain, they're working with spaces that can be infinite in some sense, but they still have a measure. And this measure has to kind of behave nicely with respect to distance.
Unbounded metric measure spaces. That sounds very abstract. Can you give me like a concrete example of what that might look like?
Yeah, sure. So you could imagine something like a fractal, like the Sierpinski gasket, for instance. This is a geometric object that has like infinite length but zero area, for example. And it also has a natural metric and a measure that kind of reflect this fractal structure. Yeah. And so these kinds of spaces with their intricate geometry, these are the spaces that the authors are setting their stage on.
Okay, so we've got these kind of exotic spaces, and we're trying to solve a Neumann problem on them. What does the Neumann problem tell us in this context?
Right. So in the classical setting, the Neumann problem is all about finding a function that satisfies a certain equation inside of a domain, given some information about its derivative on the boundary. But here, things get a little bit more nuanced because of the nature of the space and because we're dealing with this fractional operator. So instead of specifying the derivative directly on the boundary, they use this clever approach involving something called a Dirichlet-to-Neumann map.
A Dirichlet-to-Neumann map. Oh. Okay, I'm intrigued. So how does that help them define the boundary behavior?
Okay, so imagine you've got a function that's defined on the boundary of our space. Now, the Dirichlet-to-Neumann map, what it does is it takes this function and it finds its harmonic extension into the interior of the space. And then it looks at the behavior of this extension back on the boundary. And this lets them kind of indirectly specify a boundary derivative, even though the boundary itself might be very irregular.
Okay, so it's like they're building a bridge between the behavior on the boundary and the solution inside the space.
That's a great way to put it, yeah. And this bridge is really crucial for defining the fractional p-Laplacian, because what they essentially show is that you can characterize the fractional p-Laplacian through this Dirichlet-to-Neumann map.
Yeah.
So it's like they're linking it back to this Neumann problem, but in this very unusual setting.
That's a really fascinating connection. But we're still dealing with these unbounded spaces. I imagine that poses some real challenges when you're trying to solve these equations.
Oh, absolutely. Yeah. Working in unbounded spaces can be very tricky. So to address this, the authors introduce a really clever approximation scheme. Instead of working directly with the unbounded space, what they do is they consider a sequence of bounded domains that kind of exhaust the original space. So they solve the Neumann problem on each of these bounded domains, and then they carefully analyze what happens as these domains grow larger and larger.
Okay, so it's kind of like building a puzzle. You start with these smaller pieces, and then you gradually assemble the whole picture.
Yeah.
But how do they make sure that this process actually leads to a meaningful solution in the unbounded space?
Right, that's the key. And that's where some really heavy machinery from functional analysis comes into play. They use a combination of things like compactness arguments, Sobolev embeddings, and energy estimates to show that the sequence of solutions that they get on these bounded domains, they actually converge to a solution of the original problem in the unbounded space. And they have to be very careful with these estimates because, as you can imagine, the behavior of functions can get pretty wild in these unbounded settings.
I'm starting to get a sense of just how much depth there is to their work. It's not just about coming up with the right concepts, it's about actually proving that these concepts lead to well-defined solutions in these really challenging spaces.
Yeah, that's a great point. And that's one of the things that makes this paper so impressive. It's this really nice blend of these big conceptual ideas and really rigorous mathematical analysis. They don't just give us this framework for understanding fractional p-Laplacians in these exotic settings. They also prove things like existence, uniqueness, and regularity of solutions, which is no easy feat.
Okay, so we've kind of laid the groundwork here. We've explored these connections between fractional p-Laplacians, Neumann problems, and these fascinating unbounded metric measure spaces. What's the next step in this mathematical journey?
All right, so now that we've got this foundation, I think we're ready to dive into the specifics of their approach. And they use some really clever techniques here involving things like doubling measures, Poincare inequalities, and Bezoff spaces. Are you ready to explore those in a little more detail?
Absolutely.
Yeah.
I'm eager to see how all these pieces fit together. Okay, so let's dig into some of these techniques. You mentioned doubling measures, Poincare inequalities, and Bezoff spaces.
Yeah.
And those are all like pretty heavy-duty tools in analysis. So I'm curious to see how they'll come together in this context.
Yeah, they're all really important for dealing with the intricacies of these unbounded metric measure spaces. Maybe we can start with doubling measures. So these measures basically ensure that if you have a ball and you double its radius, then the mass of the ball roughly doubles as well. It's a way to control how the space grows at different scales.
Okay, so it's like preventing the space from getting too wild as you zoom out.
Exactly. Yeah. It's all about controlling the growth. Now, the Poincare inequalities, these come in when we want to relate the values of a function to its gradient. Basically, they tell us that the average oscillation of a function within a ball can be controlled by the integral of its gradient over that ball.
Okay, so it's like connecting the local behavior of the function to its overall change over a region. And these inequalities, they hold in these doubling metric measure spaces.
Yes, that's a key point. The authors rely on the fact that these spaces support what's called a p-Poincare inequality, which means the inequality holds for functions in this Sobolev space, Weber sup1 fis. And that's really crucial for establishing energy estimates and proving that their approximation scheme actually converges.
Okay, so we've got the doubling measures and Poincare inequalities. They're helping us, tame the behavior of these functions in these spaces. But where do Bezoff spaces fit into this? I know they're related to fractional derivatives, but I'm not really sure how they connect to the Neumann problem.
Right. So Bezoff spaces, they actually play a really crucial role in characterizing the boundary data for the Neumann problem. Remember that the authors are using this Dirichlet-to-Neumann map to indirectly specify the boundary behavior. Well, it turns out that the functions that live on the boundary, the ones that can be extended harmonically into the interior, these are precisely the functions that belong to a certain Bezoff space.
Oh, I see. So Bezoff spaces are giving us the right framework for describing the boundary data. That's a subtle but really important connection.
It is, yeah. And the authors, they really exploit this connection. They show that you can express the energy functional associated with the fractional p-Laplacian in terms of the Bezoff norm of the boundary data. So it's this really powerful link between the non-local operator and the behavior of functions on the boundary.
It's starting to feel like there's this really beautiful tapestry here where all these different threads, doubling measures, Poincare inequalities, Bezoff spaces, they're all kind of woven together to create this coherent picture of fractional p-Laplacians in these very unconventional spaces. But I'm still a little fuzzy on how they actually define the fractional p-Laplacian using this Dirichlet-to-Neumann map. Could we unpack that a little bit more?
Yeah, absolutely. Let's remind ourselves how this Dirichlet-to-Neumann map works, right? So you start with a function u, which is defined on the boundary. Let's call that e. And the Dirichlet-to-Neumann map, it takes this function and it finds its harmonic extension into the interior of the space, which we'll call e. We can denote that extension by ia. And this harmonic extension, it's basically the solution to the p-Laplace equation in E with the boundary condition that u equals u on the boundary eu.
Right. So oo's like a lifted version of living in this higher dimensional space, but it respects the boundary values.
Exactly. And the Dirichlet-to-Neumann map, which is often denoted by E, it takes this harmonic extension, this u, and it looks at its boundary derivative. Now, you can define this derivative in a weak sense using a test function on the boundary. So you have this center sub do sub det sub dot sub d center. And here, this is the measure on A, and this is the measure on the boundary.
Okay, so this is kind of capturing how this harmonic extension u behaves near the boundary.
Yeah.
But how do we actually get from this to the fractional p-Laplacian?
So that's where the really cool part comes in. It turns out that there's this really neat connection between this Dirichlet-to-Neumann map, this JUS, and a certain non-local energy functional. The authors show that if you take a function in the appropriate Debesov space, you have this identity, center sub bo sub dx sub dxy subsp plus d sub center, where c is some constant, d is the dimension of the space, and s is our fractional exponent. And the amazing thing here is that the right-hand side of this equation, this is precisely the energy functional that's associated with the fractional p-Laplacian.
Wow. So they connected this Dirichlet-to-Neumann map, which is defined through these local properties of the harmonic extension, to this non-local energy functional that captures these long-range interactions. It's like bridging two completely different worlds.
It is. It's a really remarkable connection. And this identity is what lets them define the fractional p-Laplacian on the boundary arrow. So they're essentially characterizing it through this Dirichlet-to-Neumann map. It's like they found a way to see the non-local operator just by looking at the local behavior of these harmonic extensions.
That is incredibly clever. But I can imagine the proof of this connection must have been pretty intense. Did they go into the details of that at all?
Oh, yeah. The proof is it's a real tour de force. It involves very carefully using all of the properties of these doubling measures and Poincare inequalities and base-off spaces that we talked about earlier. They construct this sequence of approximating domains, solve the Neumann problem on each domain, and then use compactness arguments and these energy estimates to show that these Dirichlet-to-Neumann maps that they get actually converge to the operator that they're interested in.
Wow, it sounds like a real masterpiece of analysis and geometric measure theory. I'm really starting to see why you find this paper so fascinating. They haven't just introduced this new way of defining the fractional p-Laplacian. They've actually rigorously established its properties in these really, really challenging spaces.
Yeah, you're getting it. And we're still just scratching the surface here. The authors, they go even deeper, and they explore the connection between this operator and some other really important concepts like parabolicity and hyperbolicity. These are basically ways of classifying how connected the space is, in a sense.
Okay, now my curiosity is really piqued. Tell me more about this connection between the fractional p-Laplacian and these propagation speeds. It sounds like we're about to go down an even deeper rabbit hole here.
Yeah.
So we've got this really cool connection now between the fractional p-Laplacian and the Dirichlet-to-Neumann map, all happening in these really wild, unbounded metric measure spaces. And now you're saying that this connects to even more stuff like parabolicity and hyperbolicity.
Mm-hmm.
I mean, those sound like they're describing something pretty fundamental about the space itself.
Yeah, they really are. You can think of them as kind of like classifying how connected the space is in a way. So like a p-parabolic space, this is a space where information can travel infinitely fast. But then you've got hyperbolic spaces, and those kind of impose a speed limit on how quickly things can spread.
Okay, so it's like parabolic spaces are these super highways where information can just like zip around with no problem.
Yeah.
But then the hyperbolic spaces, it's more like a local neighborhood. You know, you gotta kind of stick to the speed limit.
Exactly, yeah. That's a great way to think about it. And what the authors show is that the fractional p-Laplacian can actually detect this distinction. So in a parabolic space, the solutions to the fractional p-Laplace equation, they'll exhibit a certain kind of decay behavior as you go out to infinity, and that kind of reflects the fact that information can travel really far, but then in hyperbolic spaces, the solutions tend to be more localized, kind of confined by that finite propagation speed.
So it's like the fractional p-Laplacian is almost like the sensitive probe, right? It's kind of listening to the geometry of the space and telling us how easily things can move around.
Yeah, exactly. And this connection, it has some really interesting implications for understanding the behavior of solutions. So, for example, they prove a Harnack inequality for solutions to the fractional p-Laplace equation in hyperbolic spaces. And this inequality, it gives you these really crucial bounds on the solution. It prevents it from like growing too quickly or vanishing too quickly.
Yeah, the Harnack inequality. Yeah, I remember from some of our previous deep dives, it's a really powerful tool for kind of getting a handle on the behavior of solutions to PDEs. But I'm curious to see how it plays out in this context, with these fractional operators and these unconventional spaces.
Right. So the Harnack inequality in this setting, it takes on a slightly different form than you might see in the classical case. Instead of comparing the values of the solution at different points, it relates the integral of the solution over a ball to its infimum over a larger ball. And this modification is really necessary because of the non-local nature of the fractional p-Laplacian.
Okay, so it's still about controlling the growth of the solution, but it's kind of taking into account these long range interactions, right?
Exactly. And this Harnack inequality, it leads to all sorts of interesting consequences. So for instance, it implies that the solutions are Hölder continuous, which basically means that they can't fluctuate too wildly. And that kind of regularity, it's really crucial for understanding the fine scale behavior of the solutions and their potential applications.
This is amazing stuff. I mean, it's incredible to see how the authors have kind of brought together all these ideas from analysis and geometry and even a little bit of physics to create this really rich and insightful theory of fractional p-Laplacians. But I'm curious, like, where do they see this work leading? What are some of the open questions and the future directions that they highlight?
Well, they point out a number of really exciting avenues for future research. One really intriguing direction would be to investigate how the fractional population behaves for different values of that fractional exponent, that s. Because remember that s is really what controls the degree of non-locality, right? So as s gets closer and closer to 1, you should kind of recover the classical p-Laplacian. But that transition, between the fractional and the classical regime, it's still not fully understood.
Yeah, that makes sense. So it's like you're turning a knob on the operator and you're gradually shifting from local behavior to non-local behavior. I bet there's some really interesting phase transitions happening in that transition zone.
Oh yeah, absolutely. Another open question is to try and extend their results to even more general settings. So they focused on these doubling metric measure spaces, but there are other classes of spaces out there, like spaces with varying dimensions or spaces with different kinds of measures. And it would be really interesting to see if you could study fractional p-Laplacians in those settings as well.
Right, pushing the boundaries of the theory to handle even more exotic spaces. It's a good reminder that mathematics is always evolving, always looking for new challenges and generalizations.
Exactly. And don't forget about the potential applications. The authors, they hint at some connections to probability theory, particularly the study of jump processes. And fractional p-Laplacians could be really useful for modeling random phenomena that exhibit these long-range jumps or discontinuous behavior.
Yeah, it makes me think about applications in physics or finance or even image processing, anywhere where you need to model processes that involve these sudden changes or interactions over distances. The fractional p-Laplacian could really be a key tool.
Yeah, you're absolutely right. The framework that's developed in this paper, it really has the potential to impact a wide range of fields, and it's a testament to the power of abstract mathematics, to provide these unexpected insights and tools for tackling real world problems.
This has been a fantastic deep dive. I mean, we started with this seemingly abstract concept, this fractional p-Laplacian, and we ended up exploring this whole universe of fascinating mathematical ideas. I feel like I'm walking away with a much deeper appreciation for the beauty and the power of analysis and geometry and this interplay between the local and the non-local.
Yeah, the pleasure was all mine. It's always fun to share the excitement of mathematical discovery with someone who appreciates it and who knows what other connections and applications are waiting out there to be discovered as we continue to explore this world of fractional Laplacians.
That's the beauty of the deep dive.
Yeah.
We never know where our curiosity is going to lead us next. Thanks for joining us, and we'll see you next time for another adventure into the world of cutting-edge research. Welcome back to the deep dive. Get ready, folks, because today we're diving headfirst into some seriously advanced math.
Oh yeah, we're talking fractional P-Laplacians.
You got it. And specifically, their connection to something called Neumann problems in, get this, unbounded metric measure spaces.
So buckle up.
We're going to try. Our source for this deep dive, a real brain teaser, an academic paper that tackles this complex topic head-on.
It's a fascinating paper. It really dives into how these fractional P-Laplacians behave in a much richer, higher dimensional setting.
Okay, I'm already intrigued, but let's back up for a sec. What exactly is the equation we're dealing with here? For our listeners who might not have this stuff memorized.
Right, so the paper zeroes in on the equation, or FF.
Okay, seeing it written out, it doesn't look all that scary.
But hold on, we're talking fractional powers of the P-Laplacian here, which, trust me, adds a whole other layer of complexity.
Oh, right, and let's not forget, we're also playing in an unbounded metric measure space.
Exactly. No safety net of boundedness here.
It's like working without a net, huh?
Exactly. The paper works with a doubling metric measure space, denoted as ZDZD, which, as you said, can be unbounded.
Adding another layer of difficulty, I bet.
Definitely makes the analysis more challenging.
Okay, starting to get why this paper is considered such a big deal. It's like they chose the hardest path possible. But before we get too lost in the weeds, remind us, what are the authors trying to achieve with all this?
Well, they have three main goals. First, they want to prove that this problem is what we call well-posed, meaning that solutions actually exist, they're unique, and they depend continuously on the data you put in. Second, they're after a Harnack inequality for the solutions.
Which, for those of us not fluent in math speak, is?
It's a really powerful way to control how these solutions behave. And finally, they're trying to figure out just how smooth or well-behaved these solutions are. We call that establishing sharp regularity estimates.
So they don't just want to know if a solution exists, they want to know everything about it, its personality, its quirks.
Precisely. They're painting a complete picture.
Now, I remember skimming the paper and seeing something about structural hypotheses, kind of like setting the rules of the game.
Exactly. They lay down some ground rules about the space they're working in. Three main hypotheses, denoted as H0, H1, and H2.
Okay, hit me with them. What's H0 all about?
H0 says that the domain, which is a subset of our metric measure space, is what we call a uniform domain.
Uniform domain, so no weird shapes.
Pretty much. It means any 2 points in U can be connected by a curve that's not too long or too close to the boundary.
Got it. No mathematical dead ends. What about H1?
H1 gets into the nitty-gritty of our metric measure structure. It states that our domain with the restricted measure is doubling.
Doubling.
Meaning that if you double the radius of a ball in our space, the measure doesn't increase by more than a fixed constant.
So it's like putting a limit on how wild this space can be volume-wise.
Right. And H1 also says it supports a p-Poincare inequality.
Vaguely ringing a bell.
It essentially says that the average value of a function is related to its integral.
Okay, coming back to me now. Helps control how much the function fluctuates, right?
You got it. Provides a way to control the function's behavior based on its gradient.
And lastly, H2. What fun does that one bring?
H2 focuses on the boundary of our domain, assumes it has some key properties. It's complete, uniformly perfect, and just like the doubling property for the measure, The boundary itself is also assumed to be doubling.
The boundary has to play nice, too. Can't be too crazy.
Right. But there's more to H2. It brings in this really important relationship between the boundary and the measure.
And that would be?
It's called a codimensionality condition.
Okay, that sounds important. Lay it on me.
It's beautifully expressed in equation 1.1 of the paper.
Ah, the good old equations. Always make things clearer.
It basically tells us how the measure on the domain relates to the measure on the boundary, connects the inside of our space to its edge.
Sounds like that's going to be key later on.
Absolutely. It's this connection that lets them bridge the gap between the Neumann problem, which is defined on the boundary, and the fractional p-Laplacian, which is defined on the whole space.
Starting to see the bigger picture here. So the paper lays down these grand rules, these hypotheses, and then what's the next big step?
They dive into this fascinating link between fractional p-Laplacians and something called Dirichlet and Neumann problems.
Dirichlet and Neumann problems.
Yeah.
Okay, I'm following. But remind me what those are again.
A Dirichlet problem is like saying, the height of a function on the boundary.
Okay, like a fence around our space.
Right. And then you got to find a function that fits a specific equation inside while matching those given heights on the boundary. A Neumann problem, on the other hand, tells you about the slope of the function at the boundary.
Instead of the height. Got it. So how do they tie all this to fractional p-Laplacians?
The key is to think of our unbounded space Z as the boundary of an unbounded uniform domain.
Hold on. So the unbounded space is now the boundary. My brain's doing backflips.
I know, it's a bit of a mind bender. But it's how they connect these seemingly different concepts.
Okay, I'm trusting you here. So how do they build that bridge?
They use a really clever tool called the Dirichlet-to-Neumann map.
Catchy name.
It essentially takes the boundary values of a solution to a Dirichlet problem and gives us the normal derivative of the solution at the boundary. Transforms a Dirichlet problem into a Neumann problem.
So it's like translating between two different languages.
Exactly. And this map is absolutely crucial for building and understanding the fractional p-Laplacian on our original space Z.
So this is seriously cool stuff. So they're basically setting us up to tackle the Neumann problem first.
You got it. It becomes the stepping stone to understanding the fractional p-Laplacian.
Clever approach. Tell me more about this Neumann problem then. What's the first challenge they face?
The big one is proving that solutions to this Neumann problem exist, are unique, and stable. It's like building a foundation.
Can't build a house without a solid foundation, right?
Exactly. And the key result here is Theorem 1.4. It lays out all those crucial properties.
Theorem 1.4, huh? Sounds like a VIP in this paper. What's it say?
It says, under the structural hypotheses we talked about, and for a specific type of data, which they represent with the function f, there is one and only one solution to the Neumann problem.
So f can't be just anything.
Nope. It has to satisfy certain conditions. One is called a weighted LPO condition, essentially controls how wild the function can be.
Right, got to keep things under control. And what about stability? Why is that important?
Stability means that if you make small changes to the data, you only get small changes in the solution.
Makes sense. You wouldn't want your solution to go haywire if your data has a tiny error.
Right, it's about robustness. The paper actually gives equations for this stability. Equations 1.7 and 1.8.
Always with the equations. What do those tell us?
They give us a way to estimate how much the solutions can change based on changes in the data.
So like a mathematical safety net.
Pretty much. And the interesting thing is that these equations change depending on the value of p. Remember that from our original fractional p-Laplacian equation.
So everything's connected. I love how it all comes together.
It's beautiful, isn't it? And this stability is essential for making sure our solutions are reliable. Now, the next hurdle they tackle is the regularity of the solutions.
Regularity, so how smooth or, well, regular they are.
Exactly. And here's where we delve into the concept of Hölder continuity. It's a way to measure how smooth a function is.
Hölder continuity. Okay, I'm vaguely remembering that from my analysis classes, but a little refresher would be great.
Well, it's like a more general version of something called Lipschitz continuity. It's all about how much a function can jump between 2 points.
Right. It's coming back to me.
And Theorem 1.10 in the paper, that's all about the Hölder continuity of solutions to our Neumann problem.
So it's saying these solutions can't be too crazy?
Exactly. Under certain conditions, they have to be smooth, especially near the boundary. And the theorem even gives us a formula for how smooth they are.
I'm sensing a pattern here. Theorem, equation, theorem, equation.
It's how we build the whole mathematical framework. And understanding the regularity of the solutions is super important for actually constructing and analyzing the fractional p-Laplacian later on.
Okay, so we've explored the ground rules, dove into the Neumann problem, and touched on this Hölder continuity thing, feeling like we've laid a pretty solid foundation. Where do we go from here?
The next step is to take all this knowledge about the Neumann problem and actually build the fractional p-Laplacian on Z. This is where it all pays off.
All right, bring on the grand finale. How do they make that leap? From Neumann to fractional p-Laplacian.
They use that clever Dirichlet-to-Neumann map we talked about. They basically show that this map, when applied to the solutions of the Neumann problem, gives us an operator on our original space Z.
And that operator is, drumroll please, the fractional p-Laplacian.
Exactly. They found a secret passage between these two seemingly different worlds.
My mind is officially blown. We've gone from abstract concepts to some serious mathematical heavy lifting and uncovered a hidden connection between these seemingly unrelated problems. Incredible. All right, so last time, we laid the groundwork getting to grips with the problem and the tools these mathematicians use to tackle it. Now let's get our hands dirty and dive into the proof itself.
You game.
Born ready.
Well, the proof of Theorem 1.4, the one about the Neumann problem's well-posedness, it's a bit of a beast.
Okay, how so?
It's a delicate dance of approximation techniques and really careful analysis of convergence.
So they're not just going straight for the jugular, tackling the Neumann problem on the unbounded domain directly.
No, that would be a nightmare. Instead, they introduce a sequence of approximating domains, each with a bounded boundary we call the make.
Okay, and what do they do with those?
On each of these smaller domains, they solve a related Dirichlet problem.
Hang on, why solve a Dirichlet problem when we're after the Neumann problem?
Yeah.
Seems like a detour.
It is, but a strategic one. Solving the Dirichlet problem on each ek gives them information they can then use to attack the Neumann problem on the original unbounded domain. It's like solving a mini puzzle to get clues for the bigger one.
Divide and conquer, I like it. But how do they even solve the Dirichlet problem on these smaller domains?
Oh, they bring out the big guns, conformal transformations.
Ah, those things that preserve angles, right?
You got it. They use them to basically reshape each ek into a more convenient form.
So they're like mathematical clay sculptors, molding the domains into something easier to work with.
Exactly. And then they introduce this thing called a dampening function.
Dampening function, that sounds ominous. What's that do?
It controls the behavior of the measure near the boundary of these reshaped domains. Make sure it doesn't blow up as we get close to the edge.
Why is that so important? What happens if it blows up?
Things get messy, fast. The analysis becomes way harder. This dampening function keeps the measure well behaved, which is crucial for proving the existence and uniqueness of solutions to the Dirichlet problem.
So they reshape the domains, dampen the measure, and then what? How do they actually find the solutions?
They tap into some powerful tools from Sobolev spaces.
Those function spaces that love differential equations, right?
Right. Specifically, they use something called a trace theorem.
Okay, vaguely remember that one. What does it do again?
It connects the behavior of a function inside a domain to its values on the boundary, lets them translate information from the boundary inward.
So they're piecing together bits of information from all over.
Exactly. And that's how they prove that on each egg, there is one and only one solution to the Dirichlet problem.
But we haven't forgotten that's just a stepping stone. The real prize is the Neumann problem on the original unbounded domain.
You got it. So how do they make that final leap? Well, they have to look at what happens to these Dirichlet solutions as tri goes to infinity.
So as the ache get closer and closer to the full domain?
Exactly. The idea is that the solutions on ik should somehow converge to a solution on ik. It's like assembling a giant jigsaw puzzle.
Each ek is a piece, and as we add more pieces, the full picture emerges. I like it. But making that notion of convergence precise? That's got to be tricky.
It is. They use some serious tools from functional analysis, like weak compactness and Mazur's lemma.
Okay, those are ringing a bell, but remind me.
Weak compactness, it lets us extract convergent subsequences from bounded sequences, super useful when you're dealing with infinite dimensional spaces.
Right. And Mazur's lemma.
That one says if you have a sequence of functions that converge weakly, you can create a new sequence from them, a combination of those functions, that actually converges strongly, like smoothing out the original sequence to get better convergence.
Okay, that makes sense. So they use all this to analyze what happens to the Dirichlet solutions as the scene gets really big.
Exactly. And they show that these solutions converge to a function that's what we call harmonic in UA. a key characteristic of solutions to the Neumann problem.
So they have their candidate solution. What's the last hurdle to clear?
They got to make sure this limit function actually satisfies the Neumann boundary condition.
Right. Got to make sure it fits the rules at the edge of our space.
And here's where that codimensionality condition comes back into play.
See, I knew those ground rules would be important.
It all circles back. They prove that the gradient of this limit function satisfies a special integral identity, which basically captures the essence of the Neumann boundary condition.
And boom, they've got their solution to the Neumann problem on the unbounded domain.
It's really amazing how they connect all these different concepts.
Absolutely. But, and I know you're going to say it, this isn't the end, right? The Neumann problem was just the warm-up act.
You know it. The star of the show is the fractional p-Laplacian.
So how do they use this Neumann solution to finally get to the main event?
The Dirichlet-to-Neumann map, our trusty bridge between the two worlds.
I knew it. Always got to have a good bridge in math.
They show that the fractional p-Laplacian can actually be defined as the Dirichlet-to-Neumann map associated with the p-Laplacian on the extended domain.
So by solving the Neumann problem, they've cracked the code to understanding the fractional p-Laplacian on the original space.
You got it. They've linked a non-local operator, the fractional p-Laplacian, to a local one, the p-Laplacian, through this really elegant construction.
Amazing. This deep dive is living up to its name. We've journeyed from abstract concepts to some seriously hardcore proofs and discovered a hidden connection. What's next in this mathematical adventure?
Well, the paper goes on to explore more properties of this fractional p-Laplacian, things like stability, regularity, even a Harnack inequality, all to really solidify their construction and deepen our understanding.
This has been an incredible journey so far, but I'm guessing there's still a lot more to explore when it comes to fractional p-Laplacians, right?
Oh, absolutely. The authors actually end the paper with a whole discussion of open questions and future research directions. It's an invitation to keep digging deeper.
So even though our deep dive into this paper is coming to an end, it's clear that the exploration of these fractional p-Laplacians is just getting started.
It's a wide open field, full of possibilities.
It's pretty inspiring to think about. Well, this deep dive has certainly shown me the power and beauty of math, even when it gets really abstract.
That's what it's all about. Sometimes the most abstract ideas lead to the most profound insights.
Well said. Thank you again for being our guide through this mathematical landscape. I feel like I've learned a ton.
It's been my pleasure.
And to our listeners, thanks for sticking with us on the deep dive. We'll be back soon to wrap up this exploration of fractional p-Laplacians and talk about the bigger picture. Until then, keep exploring the infinite wonders of math. All right, we've made it. We've explored the wild world of fractional p-Laplacians, their connection to Neumann problems. We even dove headfirst into some seriously intense proofs. But now, the big question, why should we care about all this? What's the point of understanding these, let's be honest, pretty abstract mathematical objects?
You're right. It's a valid question. And while the math itself is pretty fascinating, the real power of all this lies in the potential applications.
Okay, applications. I'm listening. Give me an example. Where do these fractional p-Laplacians actually show up in the real world?
Well, believe it or not, they're popping up in a ton of different fields. Image processing, fluid dynamics, finance, even social networks.
Hold on, seriously. From abstract math to social media? That's a pretty big jump.
It is. But that's the amazing thing about math. You never know where it's going to lead.
All right, I'm intrigued. Walk me through a concrete example. How are fractional p-Laplacians used in, say, image processing?
Sure, imagine you have a blurry image you want to sharpen. The traditional methods often use local operators, which just means they only look at a small area around each pixel.
Right, like those blur or sharpen filters in photo editing software.
Exactly. But those can sometimes create weird artifacts or distortions, especially around edges or fine details.
And that's where fractional p-Laplacians come to the rescue.
You got it. They let us use non-local information, so we're not just limited to a tiny neighborhood around each pixel.
So they can see more of the image.
Exactly. And that leads to much better image sharpening algorithms, more robust, fewer weird distortions.
It's like they're filling in the gaps that those local operators miss.
Yeah.
Okay, that's one example. What about fluid dynamics? What are they doing there?
In fluid dynamics, they're used to model something called non-local diffusion processes. It's about how particles spread in a fluid over time.
So not just looking at what's happening right next to a particle, but how it's affected by things farther away.
You got it. Super important for understanding things like turbulent flow, how pollutants move in water or air, that kind of thing.
Okay, that makes sense. So we've got image processing, fluid dynamics. You said finance too, right?
Mm-hmm.
What are they up to in the world of money?
Fractional p-Laplacians can model something called jump processes.
Jump processes, like sudden changes in the stock market.
Exactly. Those sudden, unpredictable jumps in the price of an asset. Really important for things like risk management and option pricing.
I'm starting to see a pattern here. Whenever there's something complex, something with a lot of interconnected parts, fractional p-Laplacians seem to be lurking in the background.
It's true. They're a really powerful tool for understanding complex systems where things aren't just influenced by their immediate surroundings.
This is seriously cool stuff. And the fact that there's still so much research going on, new properties and applications being discovered all the time, that's pretty exciting.
It is an exciting field to be in, that's for sure.
Well, this deep dive has definitely broadened my horizons. I never would have guessed that something as seemingly abstract as fractional p-Laplacians could have such a real-world impact.
That's the beauty of math. It often starts with abstract ideas, but it can lead to some truly amazing and practical applications.
Couldn't have said it better myself. Thanks again for guiding us through this incredible mathematical landscape. I feel like I've learned a ton.
You're very welcome. Glad you enjoyed the journey.
And to our listeners, thanks for joining us on the deep dive. We hope you've enjoyed this exploration into the fascinating world of fractional p-Laplacians. And remember, whether you're a seasoned math pro or just curious about the universe, keep exploring. There's always something new to discover. Until next time. Welcome back for another deep dive. You know, we like to get into the weeds a little bit on this show, and today is no different.
Oh yeah, today's gonna be a fun one.
We are talking fractional p-Laplacians.
Ooh.
And I know that you all are very familiar with...
Yes. Our listeners are experts at this stuff.
Yeah, so...
No kindergarten math here.
We're going to just jump right in.
Yeah.
So we're going to be looking at a paper.
We're going to be dissecting a paper by Luca Capogna, Ryan Gibara, Rika Korte, and Nagaswari Shanmugalingam.
And it's just published.
Just yesterday, October 25th.
Oh, wow.
2024.
Hot off the presses.
Hot off the presses.
Okay, and the name of the paper?
Fractional p-Laplacians via Neumann problems in unbounded metric measure spaces.
Okay, so what's the core problem that they're tackling in this paper?
So they're trying to define and analyze fractional powers of the p-Laplacian. It's denoted, or 1p, but the thing is they're doing it in unbounded spaces. That might not be as nice as the Euclidean space that we're used to.
So how do we even begin to think about what kind of spaces we're working with here?
So we're talking about metric measure spaces, denoted z, d, z, e, which have a metric for distance, dzz, and a measure for size, ev. They don't even require these spaces to support a Poincare inequality.
Okay, so we're dealing with some very irregular spaces, potentially. That does make defining something like a fractional p-Laplacian pretty challenging, I would imagine.
Right, so how do they do it?
Yeah.
How do they even approach this problem?
Well, they use this really cool technique called hyperbolic filling.
Okay.
You kind of take the original space z and you fill it in with a higher dimensional space denoted x dx.
Okay, so we're embedding our potentially messy space into a higher dimensional one. What does that even accomplish?
Well, it kind of gives them a nicer environment
to
work with. They use a process called uniformization, and it smooths out the geometry of this filling to make it a uniform domain. We call this CDE. Kind of like you take a crumpled up piece of paper and you just flatten it out.
Okay, so they're creating a smoother, more well-behaved space to work with.
Exactly.
But how does that relate to the fractional p-Laplacian back in the original space?
Well, this is where it gets really neat. They establish a connection. The fractional power of the p-Laplacian in Z can be viewed as the Dirichlet-to-Neumann map for a related problem in this filling space.
Dirichlet-to-Neumann map. That does sound kind of familiar, but remind me, what exactly is that again?
So imagine you have a function on the boundary of a space. This map, it takes that function, takes the function's values on the boundary, the Dirichlet data, and it gives you information about its derivative on the boundary, the Neumann data. It relates boundary behavior to what's happening inside.
So they're translating the fractional p-Laplacian problem into a boundary value problem in this smoother space.
Exactly. And this allows them to use a lot of the established tools.
For Dirichlet and Neumann problems to tackle the fractional p-Laplacian indirectly.
And speaking of which, we should probably clarify, what's the difference between those two types of problems? Because they both deal with differential equations and boundary conditions. But what makes them distinct?
So in a Dirichlet problem, you are given the values of the solution. on the boundary. Like if you know the temperature at the edges of a metal plate,
Yeah.
a Neumann problem, you're given information about the derivative of the solution on the boundary. So like the heat flow across the edges.
Okay, so Dirichlet focuses on the solution's values,
Uh-huh.
and Neumann focuses on its rate of change at the boundary.
Exactly.
How do these problems then relate back to the paper's central goal?
Well, they focus specifically on the Neumann problem
Okay.
in this filling space, and they're able to derive stability estimates for the solutions.
Okay.
And these estimates quantify how changes in the Neumann data affect the solution.
So they're looking at how sensitive the solution is to changes in boundary conditions.
Exactly.
Why is this so crucial for understanding the fractional p-Laplacian?
It's a key step in defining and analyzing the properties of the fractional p-Laplacian back in the original space. These stability estimates help bridge the gap between the filling space and the original space.
Okay, so
yeah.
they're using stability in the Neumann problem in this filling space to shed light on the fractional p-Laplacian
Yes.
back in the original space. And what are some of the key results that they achieve?
Well, they prove the existence and uniqueness of solutions to the Neumann problem under certain conditions. And they also show the stability of these solutions. Small changes to the data lead to small changes in the solution. They prove a Harnack inequality, which gives us bounds on the ratio between the maximum and minimum values of a non-negative solution. And finally, they explore Hölder regularity, showing that under certain conditions, solutions are Hölder continuous, meaning they change smoothly without sudden jumps.
Wow, that's quite a comprehensive analysis. So how do they actually go about proving these results? Can we delve into some of the specifics?
Absolutely. They start by tackling a simplified version of the problem, the Dirichlet problem, in unbounded domains with bounded boundaries.
Okay.
To do this, they use a sequence of transform spaces. These spaces basically shrink the unbounded domain into a bounded one while preserving the key properties.
So they're making the problem more manageable without losing the essence of the original space.
Right.
What happens in these transform spaces?
Well, within each R, they apply existing results to solve a Dirichlet problem with a specific boundary data.
Okay.
They obtain a sequence of solutions, UK, but they need to ensure that this sequence converges to a meaningful solution in the original space.
How do they accomplish that?
They establish a crucial bound on the sequence's energy, preventing it from blowing up as Korte increases. They also normalize the sequence, ensuring that it's locally uniformly bounded in LP, which guarantees convergence.
So they're carefully controlling the behavior of this sequence as it approaches the solution in the original space.
Exactly. Now they apply Mazur's lemma.
Okay.
It's a powerful tool that lets them extract a new sequence with even stronger convergence properties.
Okay.
This refined sequence converges to a function, which they prove is the solution to the Dirichlet problem in the original space.
That's pretty impressive. But remember, their main target is the Neumann problem.
Right.
How do they bridge that gap?
Well, they start by focusing on the Neumann problem with compactly supported boundary data.
Okay.
Meaning the data vanishes outside a bounded set. And they use the solution to the Dirichlet problem and a transformation of the space to establish the existence of a solution to this simplified Neumann problem.
So the Dirichlet problem acts as a stepping stone.
Yes.
What about uniqueness?
Well, they prove that too,
Okay.
showing there's only one solution that satisfies the Neumann problem with this given compactly supported data. To handle the general case where the data is not compactly supported, they use an approximation scheme.
Okay. Sounds like a clever workaround. How does it work?
They construct a sequence of functions, fk, each with compact support, that approximate the original boundary data f as k increases. For each fk, they have a corresponding solution to the Neumann problem, thanks to their earlier work.
Right, so they're building a sequence of solutions based on these approximations.
Right.
But how do they know that this sequence converges to the desired solution?
This is where they invoke the uniform boundedness principle.
Okay.
By analyzing the operators associated with these solutions, they demonstrate that the sequence is bounded.
Okay.
This boundedness, combined with the convergence of the approximating functions to f, guarantees that the sequence of solutions converges to a function.
Okay.
The solution to the Neumann problem with the general boundary data f.
That's a significant accomplishment. They've tackled this challenging Neumann problem in a very general setting. Where do they go from here?
Well, they've solved the Neumann problem.
Right.
But remember, the ultimate goal is to understand the fractional p-Laplacian.
Yes. How do they connect these pieces?
Right. So remember that crucial link we talked about
Uh,
between the fractional p-Laplacian in Z
Right.
and the Dirichlet-to-Neumann map
Yeah.
in Z?
Yes.
Well, they define a new energy functional, ET,
Right.
that captures the essence of this map.
So ET acts as a proxy for the fractional p-Laplacian, allowing them to study it indirectly.
Precisely. They then prove that ET is equivalent to the standard fractional p-Laplacian energy. Minimizers of one are essentially minimizers of the other.
Okay, so it's kind of like having two different lenses to view the same object.
Right.
Choosing the one that simplifies the problem.
Exactly. And they show that the minimizers of ET are precisely the traces of those Neumann problem solutions we've been talking about.
Oh, wow. So the solutions in the filling space hold the key to understanding the fractional p-Laplacian in the original space.
That's the beauty of their approach. This connection allows them to formally define the fractional p-Laplacian in this setting. It acts on functions in the B-Sov space, and it satisfies a specific integral identity involving ET.
So they've given us a concrete definition for this operator, which was previously elusive in such complex spaces.
Right. And this definition opens up all these new avenues for analysis. We now have the tools to study the properties of the fractional p-Laplacian in this incredibly general setting.
This has been an incredible journey through some really cutting-edge mathematics. What stands out to you most from this research?
I think the sheer ingenuity in connecting these seemingly disparate concepts. You know, they take this really challenging problem in this complex space. They use hyperbolic filling to move to a smoother space, Hölder-related Neumann problem, and then they link it all back to define and understand the fractional p-Laplacian. It's a testament to the power of abstract thinking and just the beauty of mathematical connections.
I agree. It's truly inspiring. And I think it highlights that this paper isn't just about theorems and equations. It's about pushing the boundaries of human knowledge.
Yeah, it's a great reminder that mathematics is a living, breathing field. It's constantly evolving and full of surprises.
Absolutely. Well, thank you for joining us on this deep dive into the world of fractional p-Laplacians. It's been a privilege to delve into this fascinating research with you.
Yeah, it's been fun.
Until next time, keep exploring, keep questioning, and keep pushing the limits of what you think you know. Welcome back to the deep dive, ready for some serious math.
Always.
Today we're diving into fractional p-Laplacians. And knowing you, you're already way past the basics, right?
Okay, I think we can skip those.
Perfect. So let's jump right into this paper. It's called Fractional p-Laplacians via Neumann Problems in Unbounded Metric Measure Spaces.
Catchy title.
Right. It's by Capogna, Gibara, Korte, and Shanmugalingam.
Oh yeah, I've seen this one.
They connect some pretty complex ideas, but don't worry, we'll break it down.
Sounds good.
First, what does the abstract even say?
Well, they're trying to solve problems like well-posedness, the Harnack inequality, and sharp regularity for a fractional p-Laplace equation.
Okay, and what's special about this equation?
They're working in a doubling metric measure space, which could be unbounded. That makes things much trickier.
Unbounded, so like infinitely big.
Exactly. It's like trying to apply Euclidean geometry to a space that keeps expanding forever.
Whoa, that sounds tough.
It is. You need totally different tools and techniques.
So how do they do it?
They extend the Caffarelli-Silvestre method.
Which is?
It was originally for bounded spaces, but they've adapted it to work with unbounded spaces.
Clever. But how?
They use Neumann problems in something called a hyperbolic filling.
A what now?
It's like adding a whole new dimension to the problem. Imagine building a 3D model based on a 2D blueprint. That extra dimension gives them the space to work with.
So they're building a bridge between two different mathematical worlds.
Exactly.
And to do this, they're bringing in B-Sov spaces, right?
Yep. Those are essential here. They're like the trace classes of Sobolev spaces, helping connect functions on the boundary to their extensions inside the space.
All about connections, huh?
Absolutely. And they set some ground rules, too, with assumptions like H0, H1, H2, and a constant.
Those sound familiar?
They basically define the fractional power they're working with, kind of like setting the rules of the game.
So the abstract lays out a pretty ambitious plan.
It does. It's exciting stuff, though.
Now let's dive into the introduction, where they explain everything in more detail.
All right, let's see what they have to say.
They really emphasize why extending the Caffarelli-Silvestre method to unbounded spaces is such a big deal.
Yeah, it's a big leap forward. It opens up so many possibilities for studying fractional operators. Before this, it was all limited to bounded domains.
So they're breaking new ground here,
Definitely.
and they go deeper into that whole hyperbolic filling idea, right?
They explain how it relates to the original space, Z. It's a way of creating a higher dimensional space with Z as its boundary, which helps bridge the gap between the fractional p-Laplacian and the Neumann problem.
Okay, I think I'm starting to get it.
It's a lot to wrap your head around.
No kidding. But they do a good job of explaining it.
Yeah, they walk you through it step by step.
And they spend more time on Vsauce spaces, too.
Right, they explain how they connect to Sobolev spaces through something called trace. The trace of a function basically captures how it behaves on the boundary. And Vsauce spaces let us categorize functions based in how smooth those traces are.
Smooth traces. Got it.
That smoothness is crucial for understanding the fractional p-Laplacian. It's like a fingerprint that reveals a function's hidden properties.
So they've laid out the groundwork and introduced all the key players.
Yep, the stage is set.
Now let's move on to section 2, where they outline their strategy for tackling this whole thing.
All right, let's see their game plan.
They've got this 5-step process, and it's pretty clever.
I'm intrigued. Tell me more.
First, they solve the Dirichlet boundary value problem on a bounded subdomain, called EO, with boundary data belonging to a Vsauce space.
So they're starting with a smaller, more manageable piece of the puzzle.
Exactly. And they're looking for a solution in the D1P space.
Which means the solution needs to have well-behaved derivatives.
Right. It's all about finding a function that fits the pattern on the boundary without getting too wild in the middle.
Makes sense. What's step 2?
Then they tackle the Neumann boundary value problem, but on a transformed version of that subdomain, they actually change the metric and measure of the space, which makes the problem easier to handle.
It's like changing your perspective to get a better view of the problem.
Exactly. They simplify things further by starting with boundary data that's nicely contained within a ball and has a zero average.
So they're starting with a very specific, well-controlled scenario.
Yep. Building up from the simplest case.
Smart move.
Then in step 3, they extend their solution to more general boundary data. They do this by solving the Neumann problem on a bunch of subdomains that gradually fill up the entire space.
So it's like piecing together a giant jigsaw puzzle.
Exactly. Solve each piece, then put them all together.
I like it. What about steps 4 and 5?
Step 4 is where they use the power of compactness. This lets them show that all those solutions on the smaller pieces actually converge to a solution for the whole unbounded domain.
Compactness is a powerful tool. It basically guarantees that a sequence of well-behaved functions will have a well-behaved limit.
So they're not just solving pieces of the problem, they're making sure those pieces fit together to form a coherent whole.
Very elegant. And step 5.
Finally, they prove that this solution is unique. Well, unique up to a constant. And they also show that the solution changes continuously with the data.
Meaning if you tweak the boundary data a little, the solution only changes a little.
Exactly. They've laid out a really impressive plan, and it seems like they've thought of everything.
It does. I'm eager to see how they execute this plan.
Me too. Let's dive into section 3, where they equip us with all the math tools we'll need for this adventure.
Sounds like we're going on a mathematical treasure hunt.
Right. And we need the right gear.
Lead the way.
First up, a reminder about the doubling property of a measure.
Ah, yes. That ensures the measure of a ball doesn't explode when you double its radius. Pretty crucial in metric measure spaces.
Right. Keeps things from getting too out of hand. Then they talk about codimensionality, which is all about the relationship between the measure on the boundary and the measure in the domain.
Kind of like comparing the edge of the space to its interior.
Exactly. Then we've got our trusty Sobolev type spaces and Poincaré inequalities.
Those are essential for studying functions and their derivatives, especially when we're going beyond those familiar Euclidean spaces.
Right. Those are our bread and butter. And then, of course, Vsauce spaces, which we've already touched upon. Remember, they help us classify functions based on the smoothness of their traces.
Like I said, smooth traces are key.
And we can't forget about the trace and extension theorems.
Ah, yes. Those are the bridge builders. They connect functions defined on the boundary to their extensions inside the space.
Like having a secret decoder ring.
Exactly. And what's next on our list of tools?
Uniform domains. Spaces with nice geometric properties that make them well-behaved for analysis.
Uniform domains have a good balance to them. No weird bottlenecks or pinch points.
Right. Everything flows smoothly. Then we delve into differentiable structures, specifically Cheeger differential structures.
Those are a way of defining derivatives in more general settings, where the usual calculus rules might not apply.
Right, because not every space is as nice and smooth as a Euclidean space.
Exactly. Sometimes things get a little rough around the edges.
But those Cheeger differential structures help us navigate those rough edges and still make sense of derivatives.
They're essential for understanding harmonic functions, right?
Absolutely. And they remind us of a key property of harmonic functions, conformal invariance.
Which means they stay harmonic even if you transform the space in certain ways.
So their harmony is preserved, even if you change the tuning.
I like that.
Okay, it's a lot of tools. Now let's move on to section 3.8, where they start laying the groundwork for their main results.
Time to put those tools to use.
They start by establishing an equivalent formulation of the Neumann problem.
This is where they connect the Neumann problem, which is about boundary values, to an energy minimization problem.
So it's like saying finding the most stable configuration of a system is the same as solving certain equations.
Exactly. It's a powerful connection.
And to make sure they're on the right track, they connect their work back to the familiar Euclidean setting in corollary 3.11. This shows that their approach aligns with the Caffarelli-Silvestri framework in simpler cases.
Always good to have a sanity check.
Now let's jump to section 3.9, where they start building towards their goal of solving the Neumann problem in a more general setting.
Okay, let's see how they handle this.
First, they tackle the Dirichlet problem in unbounded domains with bounded boundaries.
So they're still easing into the full complexity of the problem.
Exactly. Baby steps. They start with a transformation that changes the metric and measure of the space. This basically compactifies the domain, making it easier to analyze.
It's like shrinking an infinitely large map onto a finite piece of paper.
Perfect analogy. And theorem 3.14 assures us that this transformation doesn't mess things up too badly. The transformed space still has all the nice properties we need.
So it's a faithful representation of the original problem, just in a more convenient package.
Exactly.
What's next?
Then comes lemma 3.15. Which shows that the Sobolev spaces on the original and transformed domains are essentially the same.
So we're not losing any information by working with this mini version of the problem?
Right, it's like a compressed file that still contains all the original data.
I see. And what about the main result for the Dirichlet problem in this setting?
That's theorem 3.16. It guarantees that for any given boundary data, there's a unique solution to the Dirichlet problem in the transform space.
So they've got a solid foundation for tackling the more challenging Neumann problem.
Exactly. And they introduce another powerful tool, the uniform boundedness principle, also known as the Banach-Steinhaus theorem.
That's a classic. It's all about controlling the behavior of families of linear operators.
Right. If the operators are well behaved on individual elements, they're well behaved on the whole space.
A very useful principle.
Okay, we've got all our tools and some promising results. Are you ready to tackle the Neumann problem head on?
Bring it on. Now things get really interesting. Section 4 dives into the Dirichlet problem, but this time both the domain and its boundary are unbounded.
No more compactified version.
Nope, we're in the wild west of unbounded domains now.
How they handle that?
They build a sequence of domains, each with a bounded boundary, that gradually expand to fill up the whole space.
Like a set of Russian nesting dolls getting bigger and bigger.
Exactly. Each one a step closer to that infinite doll.
But how do they make sure these dolls are well behaved?
Lemmas 4.2 and 4.3 are key. Lemma 4.2 shows that each subdomain inherits the nice properties of the original domain, like uniformity and the Poincare inequality.
So they're still working in a nice space, even though it's getting bigger.
Right, and Lemma 4.3 proves that the Sobolev space on each subdomain is essentially the same as the Sobolev space on the whole domain. So they're not losing any expressiveness by working with these smaller pieces.
It's like using a smaller map to navigate a bigger territory, but the map still shows you all the important landmarks. So what do they do with these dolls?
They apply theorem 3.16 to each one.
The one that guarantees a unique solution for the Dirichlet problem in a bounded setting.
That's the one. Now they have a unique solution on each nested doll.
And they're using the Caffarelli-Silvestri method each step of the way, right?
Precisely. Inch by inch, they're approaching the solution on the unbounded domain.
Clever. So what do they know about these solutions?
They show in equation 4.4 that the solutions satisfy a specific integral equation.
Anything special about this equation?
It involves test functions that can have non-zero values at infinity.
So they're not restricting what happens at the edge of the space.
Right, they need that flexibility when dealing with unbounded domains.
Makes sense. What else?
They establish some important bounds. Equation 4.5 bounds the p-energy of the solutions.
So they're controlling how much the solutions can vary as they move from one subdomain to the next.
Yeah, like setting a speed limit so the energy doesn't blow up as they approach the unbounded domain.
And then lemma 4.6 gives us a bound on the solution's LP norm, but with respect to a transformed measure.
This ensures the solutions stay well behaved in terms of their overall size.
So they're being very careful to keep everything under control. Where does all this lead?
To proposition 4.7, the culmination of this section.
The big reveal.
Exactly. This proposition proves that a solution to the Dirichlet problem exists on the whole unbounded domain.
So they've shown that as those nesting dolls grow, the solutions converge to a well-defined solution on that infinite doll, which represents the entire unbounded domain.
Right. And equation 4.8 summarizes the key properties of the solution. It matches the boundary data and satisfies a specific integral equation.
So they found a solution. Is it the only one?
That's where section 4.3 comes in. They use properties of p-harmonic functions and the fact that p is greater than 1 to show that this solution is essentially unique.
No other solution fits the bill.
Yeah.
Impressive. So they've conquered the Dirichlet problem in this unbounded setting.
They have. Now it's time to face the main challenge, the Neumann problem.
The big boss.
They start by focusing on the Neumann problem with compactly supported boundary data in section 5.
So back to simplifying things a bit before tackling the full complexity.
Exactly. Proposition 5.1 is their first victory in this section. It proves that for well-behaved boundary data, a solution to the Neumann problem exists.
And I bet they also show that it's unique, up to a constant.
You know it. They also introduce a new tool in Corollary 5.3, a bounded linear operator associated with the boundary data. They connect the norm of this operator to the D1P norm of the solution.
So they're linking properties of the boundary data to properties of the solution.
Exactly. And this connection holds even for non-compactly supported data as long as a solution exists, which hints at their approach in the next section where they tackle the more general case.
Okay, bring on section 6.
This is where their ingenuity shines. They introduce a weight function, J, to control the behavior of the solutions. Think of it as a scaling factor that adjusts for the unboundedness of the domain.
So they're giving different parts of the space different weights because it extends indefinitely.
Exactly. Then they create a sequence of approximations to the boundary data, each with compact support, that gradually approach the original data as k increases.
Like drawing increasingly detailed maps of a vast territory, starting with a rough outline and then filling in the details.
A perfect analogy. Lemmas 6.2 and 6.8 show that these approximations are well-behaved and converge to the original data. Lemma 6.2 ensures they're bounded, and lemma 6.8 establishes convergence in a weighted LP's norm using that weight function J.
So these maps are accurate and consistent.
Precisely. And Corollary 6.11 confirms that they form a Cauchy sequence, meaning they're getting closer and closer to each other.
A well-defined limit is on the horizon.
Exactly. Now they can apply proposition 5.1, the result for compactly supported data, to get a sequence of solutions, each corresponding to one of those approximations.
So they're using their previous victories to conquer this bigger challenge.
That's the strategy. Equation 6.2 foo shows that these solutions satisfy a specific integral equation, and lemma 6.13 bounds their D1P norm independently of k. This bound is crucial for proving convergence.
So they're showing that the solutions as a whole are well-behaved.
Right. They're not going haywire as ek increases.
What's next?
They leverage weak compactness. Lemma 6.15 shows that the gradients of these solutions form a Cauchy sequence. This means the gradients are converging, but in a weaker sense.
So the slopes of the solutions are aligning, even if the solutions themselves aren't converging in the usual way.
Precisely. But they want a stronger result. So they introduce a normalization technique in lemma 6.21 to ensure the solutions stay bounded, which helps them get that stronger convergence.
Okay, they're not settling for weak convergence.
Nope. And this leads to proposition 6.22, the grand finale of this section.
A final boss.
You could say that. This proposition proves that a function exists belonging to D1P that solves the Neumann problem for the original non-compactly supported boundary data.
So as those maps become more detailed, the solutions converge to a function that solves the problem on the whole unbounded domain.
Exactly. They've conquered the Neumann problem in a very general setting. Pretty impressive, right?
Absolutely. But what about stability?
Ah, that's the focus of Section 7. They want to know how sensitive the solution is to changes in the boundary data.
So if you tweak the boundary conditions, does the solution go crazy or does it stay relatively stable?
Exactly. They analyze the continuity of the solution with respect to the weighted LP norm of the data using that weight function J again.
Makes sense, since J helps handle the unboundedness.
Right. Lemma 7.1 establishes an a priori estimate that connects the D1P norm of the solution to the weighted LP norm of the data.
So they're showing that the energy of the solution is controlled by the weighted energy of the data.
Precisely. This suggests that small changes in the data shouldn't cause wild swings in the solution.
Fingers crossed.
Proposition 7.3 then dives into the stability question, proving continuity of the solution with respect to the data in the weighted LP's norm.
So they're showing that small changes in the data lead to small changes in the solution.
Exactly. They handle two cases, p greater than or equal to 2 and p between 1 and 2. Each case needs a slightly different approach.
They're being thorough.
Always. The key takeaway is that they establish continuity in both cases.
So their solutions to the Neumann problem are robust, not overly sensitive to small perturbations.
Exactly. And Theorem 7.8 summarizes the stability result, giving explicit estimates that quantify how much the solution can change based on the data.
So they've proven stability and quantified it.
Precisely. Now they've thoroughly explored the Neumann problem, it's time to circle back to the fractional p-Laplacian.
Back to the original mission.
Section 8 takes us back to space Z, where they want to define and analyze the fractional p-Laplacian.
Time to connect all those insights about the Neumann problem to the original goal.
Exactly. They start with Theorem 8.1, a uniformization result that lets them view Z as the boundary of a well-behaved uniform domain. This is crucial because it lets them use all their results for the Neumann problem on that domain.
So they've built a bridge between the world of Z and the world of the Neumann problem.
Exactly. Then comes definition 8.2, their definition of the fractional p-Laplacian on Z. It's based on a nonlinear form that captures the essence of the Dirichlet-to-Neumann map.
So they're using the Neumann problem to define the fractional p-Laplacian.
Precisely. They've translated their understanding of the local problem to the non-local setting.
Clever. But is this definition legit?
Lemma 8.3 shows that their new energy form is equivalent to the classical Bisov energy.
So their definition aligns with the existing understanding of the fractional p-Laplacian.
Exactly. And proposition 8.4 further solidifies the connection to the Neumann problem. It says that the minimizers of a specific fractional p energy are precisely the traces of solutions to the Neumann problem.
So the Neumann problem holds the key to understanding the fractional p-Laplacian.
It's a beautiful connection. Then definition 8.7 formally defines the domain of the fractional p-Laplacian, and remark 8.8 emphasizes the role of that Dirichlet-to-Neumann map, cementing the bridge between the local and non-local worlds.
Wow, what a journey. They've tackled complex concepts, developed clever strategies, and achieved their goal of defining and analyzing the fractional p-Laplacian in this challenging setting.
It's a testament to the power of mathematical thinking.
Absolutely. Well, that wraps up our deep dive into this fascinating paper.
It's been a pleasure exploring these ideas with you.
Likewise. We've seen how mathematicians can push the boundaries of our understanding, revealing deep connections between seemingly disparate concepts.
And who knows what other discoveries await us in this exciting field.
That's the beauty of mathematics. There's always more to explore.
Thanks for joining us on this deep dive. We'll be back soon with another adventure into the world of cutting-edge research. Until then, keep those mathematical minds engaged. So they've tackled existence and uniqueness. But what about stability? If you tweak the boundary data, does the solution go haywire?
That's what they look at in Section 7. They want to see how sensitive the solution is to those changes.
Does it stay stable or freak out? Right. They analyze how continuous the solution is, looking at the weighted LP norm of the boundary data.
With that weight function J again.
Yep, J's still crucial here. Remember, it helps deal with the unboundedness of the domain.
Right.
They start with lemma 7.1, which gives them an estimate that links the D1P norm of the solution to the weighted LP norm of the data.
So they're showing that the solution's energy is controlled by the weighted energy of the data.
Exactly. Small changes in the data shouldn't lead to massive changes in the solution.
That's good news.
Then proposition 7.3 dives into the stability question directly, proving the continuity of the solution with respect to the data in that weighted LP norm.
So small changes in, small changes out.
Precisely. They handle two cases separately, depending on the value of P.
Makes sense. They always seem to be very thorough.
They are. But the main takeaway is that they prove continuity in both cases.
So their solutions are robust.
Exactly. They don't overreact to small changes in the boundary data.
That's reassuring.
And Theorem 7.8 sums up their stability result, giving explicit estimates for how much the solution can change based on the data.
So they've not only proven stability, but actually quantified it.
Precisely.
Impressive. Now, they've spent a lot of time on the Neumann problem. What about the fractional p-Laplacian? That was the whole point, right?
It was. And they haven't forgotten about it. Section 8 brings us back to the original space Z, where they'll define and analyze the fractional p-Laplacian.
So all that work on the Neumann problem is finally paying off.
It is. They start with a uniformization result, Theorem 8.1, which lets them view Z as the boundary of a nice uniform domain. This is crucial because it allows them to use all their results about the Neumann problem.
They've built a bridge back to the original problem.
Exactly. Then they define the fractional p-Laplacian on Z in definition 8.2. It's based on a nonlinear form that captures the essence of the Dirichlet-to-Neumann map.
So they're defining the fractional p-Laplacian using the Neumann problem.
Precisely. They've taken what they learned about the local problem and applied it to the non-local setting.
Pretty slick. But is this a valid definition?
Lemma 8.3 shows that their new energy form is equivalent to the classical Beesov energy, so it aligns with existing understandings of the fractional p-Laplacian.
Okay, so they're not just making things up.
Nope. And proposition 8.4 further connects their definition to the Neumann problem. It states that the minimizers of a specific fractional p energy are precisely the traces of solutions to the Neumann problem.
The Neumann problem really is the key to understanding the fractional p-Laplacian.
It is. Then definition 8.7 formally defines the domain of the fractional p-Laplacian on Z, and remark 8.8 emphasizes the role of the Dirichlet-to-Neumann map, solidifying that connection between the local and non-local worlds.
Well, this paper has been quite a journey. We've gone deep into the Neumann problem, explored its properties, and finally connected it all back to the fractional p-Laplacian.
It's a beautiful example of how mathematicians can build bridges between seemingly different areas of math.
It shows the power of abstract thinking and the elegance of mathematical connections.
Absolutely. This paper has opened up new avenues for understanding fractional operators in more general settings. Who knows what other discoveries await us?
That's the beauty of math. There's always something new to explore. Thanks for joining us on this deep dive into the world of fractional p-Laplacians. We'll be back soon with another exciting adventure into cutting-edge research. Until then, keep those mathematical minds engaged. Welcome back, everyone, to another deep dive. We've got some really fascinating math to dig into today.
Looking forward to it.
You sent in this paper, and it's titled Fractional P-Laplacians via Neumann Problems in Unbounded Metric Measure Spaces.
Right.
And I got to say, this one's a real head-scratcher. In a good way, of course. Ready to unravel how these fractional P-Laplacians behave in unbounded spaces.
Absolutely. It's definitely a pretty fascinating area of research, especially since most of the previous work has been limited to bounded spaces, which are much easier to work with. This paper really takes things to the next level.
Right, so let's set the stage here. The paper introduces a new method for constructing these fractional powers of the p-Laplacian, and they're working with, let me get this right, doubling metric measure spaces.
Yeah, exactly. Denoted as Z, DZ, Z.
Z, DZ, DZ, okay.
Which should be unbounded, right?
Precisely. That's a key point.
Right.
And what makes this paper even more interesting is that it goes beyond previous work on bounded spaces and actually drops a key assumption that Z supports a Poincare inequality. Why did they decide to do that?
Well, it's all about pushing the boundaries, right? By working in this more general setting, the authors are able to capture a wider range of phenomena and potentially discover deeper connections between different areas of mathematics. They achieve this by viewing an unbounded space Z as the boundary of a uniform domain.
Hold on. Uniform domain.
Yeah. And this domain lives within what's called a kind of a special hyperbolic filling of Z.
Hyperbolic fillings. That sounds like something straight out of Star Trek. Can you explain that a bit more? I mean, what does that even mean?
It's basically a way to embed our unbounded space Z into a larger curved space, kind of like putting a 2D map onto a 3D globe. In this curved space, we have more tools and techniques at our disposal to analyze things.
Interesting.
You know, you might see some connections to Gromov's work on hyperbolic groups and spaces here.
Ah, Gromov. Now that's some serious math. But how does all of this connect back to something more down to earth. Something like Bisov spaces, for example.
That's what's so cool about this paper. It ties those abstract concepts to more familiar ground. In this case, Bisov spaces appear as trace classes of Sobolev spaces on that honor main we were talking about.
Right. Okay, so I think I'm starting to get the bigger picture.
Yeah.
But the paper also introduces these three key conditions, HEO, H1, and H2. What are those all about?
Think of them as the rules of the game. They ensure that we're operating within a well-defined mathematical environment, that things make sense. They provide the necessary structure and regularity.
Okay, and then they focus on the Neumann problem, right?
Yeah.
Could you quickly explain what that is and how it connects to all this?
Sure. The Neumann problem basically asks, can we find a function that satisfies a certain partial differential equation inside a given domain with a specific behavior on the boundary?
Okay.
In this case, the equation involves the p-Laplacian, which is a generalization of the regular Laplacian operator.
Right. And what's so special about this Neumann boundary condition?
The Neumann boundary condition dictates the value of the normal derivative of the function on the boundary. In this case, it's expressed as Excerpts nu f on the boundary. So this condition essentially links the function's behavior near the boundary to the data f that we're given.
Got it. So we're trying to find a function that satisfies the p-Laplace equation inside the domain and has this particular relationship with the data f on the boundary. How do fractional p-Laplacians enter the picture?
Well, that's where things start to get really fascinating. The paper constructs these fractional powers of the p-Laplacian by connecting them to solutions of the Neumann problem.
Okay, this is starting to get good.
Yeah.
Let's talk about Theorem 1.4, which seems to be a key part of their approach. What are the main points?
Right. Theorem 1.4 establishes the existence, uniqueness, and stability of solutions to the Neumann problem within the framework set up by H0, H1, and H2.
Okay, that makes sense.
Essentially, it says that for a given set of boundary data F, we can find a unique solution U. And this solution behaves predictably when we change the data F a little.
So they use that as a starting point to then define the fractional p-Laplacian.
Precisely. It's the foundation for everything that follows.
Okay, and then Theorem 1.10. This one dives into the regularity of solutions. Can you break down what regularity means here and why it matters?
So regularity, in simple terms, refers to how smooth the solutions are. How well behaved are they in terms of their derivatives. Theorem 1.10 explores the Hölder regularity of solutions close to the boundary. It quantifies how smooth they are as we get closer to that boundary.
I see. And what are the key factors influencing this smoothness?
Well, the theorem points out several crucial elements. The lower mass bound exponent Q, the integrability condition on the boundary data F, and the Hölder exponent F, which is a direct measure of that smoothness we were talking about.
So Theorem 1.10 basically gives us a way to assess how well-behaved solutions are near the boundary.
Exactly. And it helps us understand the interplay between the measure, the boundary data, and the smoothness.
Fascinating. But before we go too far, can we step back and talk about where fractional Besov energy fits into all of this?
Great question. So the paper introduces this alternative fractional Besov energy, denoted by EP, and it shows how their approach aligns beautifully with the Caffarelli-Silvestre method.
And that method is?
It's basically a way to study these non-local operators, like our fractional p-Laplacian, by relating them to local operators in a larger space.
Right, okay.
The form ET, given by equation 1.12, plays a crucial role in connecting these different concepts.
Right, so they're building these connections between fractional p-Laplacians, the Neumann problem, and fractional Besov energies, all within the framework of unbounded spaces.
Precisely.
My mind is officially blown. But we've covered a lot of ground already, and I think we need to give everyone a chance to process all this information. We'll be back soon to dive into Theorem 1.18 and explore its implications. Stay tuned.
Looking forward to it.
Okay, so we're back and ready to dive even deeper into this mathematical rabbit hole. We left off talking about Theorem 1.18, which I've heard is kind of a big deal in this paper.
You're absolutely right. Theorem 1.18 brings everything together and really showcases the remarkable properties of the fractional p-Laplacian.
Yeah.
Okay,
let's break it down. What are the main takeaways?
First, it establishes a really beautiful connection between the form ET, which we touched on earlier, and the fractional Besov energy EP.
Right, I remember that.
It shows that these two seemingly distinct mathematical objects are actually capturing the same core properties of functions within this homogeneous Besov space, HPPZ.
Okay.
And this equivalence really depends on the doubling property of the measure. It's all interconnected, you see.
I'm starting to see that, yeah. But what about the fractional p-Laplacian itself? What does this theorem tell us about how it behaves?
That's where things get really interesting. Theorem 1.18 establishes three crucial properties of the fractional p-Laplacian. First, it states that there's a unique solution of within this homogeneous B-soft space, HBPPZ, for a given function f that satisfies certain conditions.
So for the right f, we can always find a unique function f that solves the fractional p-Laplacian equation.
Exactly.
Hold on, though. The paper mentions unique modulo a constant. What does that mean again?
It basically means there might be multiple solutions, but they all differ by, at most, a constant value. Think of it like finding a function that solves a derivative equation. If you add a constant to that function, it'll still solve the equation.
Right. So it's the same concept here.
Yeah, exactly. So existence and uniqueness, modulo a constant, that's our first big takeaway.
Okay, got it. What's the second takeaway?
The second part looks at the stability of these solutions. It provides an estimate in equation 1.1f that tells us how much the solution f changes when we slightly adjust the data f.
Okay, and why is that important?
It's important for applications because it guarantees that small errors in the data won't cause huge changes in the solution. It's like a mathematical safety net.
I like it, a mathematical safety net. And what's the third big takeaway? Something about a Harnack inequality, right?
Yes. The third part introduces a Harnack inequality for solutions of the fractional p-Laplacian. It basically says that for a non-negative solution, its maximum and minimum values within a certain ball are comparable.
So it sets bounds on the solution's behavior.
Exactly. It helps us control how much the solution can fluctuate within certain regions.
This theorem 1.18 is packed with information. It establishes existence, uniqueness, stability, and even bounds on the solutions. But are there any limitations to this theorem?
Well, like any powerful theorem, it does come with certain assumptions. Like the theorem relies on those conditions we talked about earlier, H1, and H2. If we loosen those conditions, we might get different results, or we might need different mathematical tools to analyze the problem.
So there's still more to explore beyond the scope of this theorem.
Absolutely. That's what makes it so exciting. There's always more to discover.
Okay, what about the proofs themselves? Anything particularly innovative there?
They're a really clever blend of classical and modern techniques. They use tools from potential theory, metric geometry, and harmonic analysis. One really cool aspect is how they use extension techniques, drawing inspiration from the work of Caffarelli and Silvestri.
And how do those extension techniques work?
They cleverly link the fractional p-Laplacian on the boundary Z to a local p-Laplace type operator on that extended space. It lets them use existing theory for local operators to study the non-local fractional p-Laplacian. Pretty neat, right?
Very. And what about the challenges of the unbounded setting and the lack of a Poincare inequality? How do they deal with those?
That's where their ingenuity really shines. They came up with new approaches and used more advanced techniques. For instance, they employed delicate covering arguments and carefully designed test functions to overcome the lack of compactness that usually comes from the Poincare inequality.
So they really pushed the boundaries of the theory and the methods.
They did. It's really impressive work.
Okay, let's zoom out for a second. What are the bigger implications of this research? How does this connect to other areas of math or potential applications?
Well, one really exciting area is non-local diffusion processes. You can think of the fractional p-Laplacian as the generator of a specific type of jump process. This can be used to model things in physics, finance, and even other fields. There's also the study of fractional Sobolev spaces, which are closely tied to fractional p-Laplacians.
So this research has implications not just in pure mathematics, but also in other fields like physics and finance.
Exactly. It really shows how these abstract mathematical ideas can help us understand the real world.
This has been an amazing deep dive. We've learned so much about fractional p-Laplacians, their connection to the Neumann problem, and those remarkable properties in Theorem 1.1 But there's still a few more things to discuss, right? Like those interesting remarks at the end of the paper.
Right. Those remarks hint at some open questions and potential directions for further research, and I think they're worth exploring.
Perfect. Let's move on to those remarks and see what else we can uncover. Okay, so we've made it to the final stretch of this mathematical marathon. We've covered a lot of ground, but those remarks at the end of the paper really caught my eye. They seem to point to some open questions and maybe even some new research directions.
Yeah, you're right. Those remarks are like little seeds of mathematical curiosity, just waiting to sprout into something bigger. They show us that even with a powerful result like Theorem 1.18, there's always more to explore.
Right. Okay. So let's start with remark 1.20. It asks, what happens if we relax that integrability condition on the data f? Basically, what if we allow f to be a bit more, wild?
That's a really interesting question. It pushes the limits of the theory and asks whether we can still guarantee existence and regularity of solutions when the data isn't as well behaved. It's like testing the robustness of the mathematical framework they've built.
And what could be the implications of relaxing that condition? Could we see new types of solutions, or would we need completely new math tools to even analyze it?
That's the exciting part. It's a bit of a mystery, and that's what makes it so intriguing. It could lead to entirely new discoveries or force us to develop new techniques to deal with the added complexity.
Okay, so remark 1.20 poses a what-if scenario. What about remark 1.16? It talks about the choice of Cheeger differential structure.
Right, and that's basically how we define derivatives in this abstract metric measure space. What's fascinating about remark 1.16 is that it highlights how different choices for this Cheeger structure actually give us a whole family of fractional operators.
So it's like we have a set of different fractional p-Laplacians.
Exactly, and they all act on the same homogeneous B's off space, HBPZ.
So does that mean the properties of the fractional p-Laplacian, like the existence and uniqueness of solutions, could change depending on which structure we choose?
That's a great question. And it suggests that the behavior of the fractional p-Laplacian isn't just determined by the space in the exponent herd. The choice of differential structure matters too. It opens up a whole new area of investigation, looking at how that choice affects the operator and its solutions.
This is really fascinating stuff. Now, I'm curious, how do these results relate to previous work on fractional p-Laplacians, especially in those cases where z is doubling and supports a Poincare inequality?
That's a good question. The authors address that in Section 9. They discuss the connections to existing research, pointing out both the similarities and differences between their approach and what's been done before. They show that in certain cases, their construction actually recovers known results, while in other cases, it extends those results to a more general setting.
I like that. So they're building on existing knowledge and expanding it at the same time.
Exactly. And Section 9 is a really helpful guide to the relevant literature. It shows how the ideas and techniques in this field have evolved over time.
Well, this has been a truly incredible deep dive. We've explored fractional p-Laplacians in unbounded spaces, their connection to the Neumann problem and fractional Bezoff energies, and that powerful theorem 1.18. But now I'm even more curious about what's next. What unanswered questions or unexplored areas do you find most interesting?
That's the beauty of mathematics, right? Every answer leads to more questions. Personally, I'm fascinated by the implications of those remarks we talked about. What happens when we relax that integrability condition? How does the choice of Cheeger structure really impact the fractional p-Laplacian? There's so much more to investigate.
We're like explorers at the edge of a vast, uncharted mathematical territory.
Exactly. And who knows what amazing discoveries await us as we venture further. Maybe new types of solutions, new techniques, or even unexpected connections to other areas of math. The possibilities are truly endless.
This deep dive has been an absolute thrill ride through the world of fractional p-Laplacians, and it's been a privilege to have your expertise guiding us along the way. Thank you so much for joining us and sharing your insights.
The pleasure was all mine. It's always exciting to discuss math with someone who's as enthusiastic about it as you are.
To all our listeners, thank you for joining us on this deep dive. We hope you found it as fascinating and thought-provoking as we did. Until next time, keep exploring, keep questioning, and keep pushing the boundaries of mathematical knowledge.